Okay, so we're going to continue talking about the Java ExecutorService. What I'm going to do today is give you a very detailed walkthrough of an example that actually illustrates how this stuff works. This is a variant or revision and an improvement to the PrimeChecker app that we looked at last time. And this time, rather than using the very simplistic executor interface, it uses the much more powerful ExecutorService interface. So let's kind of give a recap of what this app's trying to do. If you recall, it's an embarrassingly parallel app that's going to use the ExecutorService to determine whether n random numbers are prime. So that's basically the functionality it does. I recommend you take a look at it. It's really cool. I'm going to walk through selected highlights, but the actual implementation is more interesting than we'll be able to show in the highlights that we explained. This example, unlike the previous one, also shows how to handle runtime configuration changes in Android. What that means is when you take your Android phone and you rotate it, it goes from landscape to portrait mode or vice versa. And that causes certain things to get shut down and restarted. Activities get shut down and restarted. And we want to make sure that our program is robust to those kinds of changes. So it shouldn't have to do anything to stop the computation, even though the world is shifting from one orientation to the next. The other thing that we're going to show here is how to interrupt threads. And the idea is that when someone clicks on the cancel button here on the UI, we want that to cause the threads that are running to be shut down. In fact, the thread pool to be shut down so that we can clean things up and restart it again with a new run. We'll talk more about thread interruption in more detail later. I'll give you a quick overview in these slides, but we'll talk about it in a more systematic way at some point down the road. OK, so how does this work? Under the hood, it uses the ExecutorService. And this particular ExecutorService is implemented as a fixed size thread pool. So as you can see, we're going to say executors, that's the utility class, .new fixed thread pool. And we give it the number of processor cores that the virtual machine thinks are on this hardware device. So let's say it's 4 for sake of argument. So we have 4 cores. We'll end up with 4 threads, and it's a fixed size pool. And this is actually kind of a picture of what things are going to look like in our program. So we're going to have a stream of random numbers. We're going to be giving callables to the thread pool, which is going to be a thread pool executor under the hood. That's what implements new fixed size thread pool. That'll have 4 threads. In this case, just for sake of argument, we're going to end up queuing up the callables so that they can be processed when there's an available thread in the pool. And as things finish, we're going to put a list of futures in a data structure which will be used to keep track of the results of the computations as they finish. Now, if you were to take a peek inside of new fixed thread pool, if you were to look at the implementation of this method, and we'll come and look at that later in the course, but if you were to do that, you would find that the fixed size thread pool in the executors interface uses an unbounded queue. It uses a linked blocking queue as opposed to an array blocking queue, which has a fixed size to it. And the reason for doing this, as I mentioned last time, is to avoid deadlocks. So how the heck could you end up with a deadlock with a fixed size queue? And how does an unbounded queue solve that problem? Because this uses an unbounded queue as opposed to a bounded queue. So here's one way this could happen. Imagine, for sake of argument, that we've got 4 threads. And let's say, again, for sake of argument, we've got some fixed-sized queue. Let's say it's 4, although the fact that they're both 4 doesn't really matter for this discussion. So we end up putting some items into the queue. The threads start to run. Let's say that there's a bunch of other threads that are putting things into the queue. In fact, let's say that these threads in the pool are creating new tasks and sticking them into the queue. Right? So not only is the outside world thread putting things in the queue, but the threads inside the pool can also create new tasks and stick them in the queue as well. Well, you can imagine if you've got 4 threads running and all 4 threads go and try to put things in the queue, and the queue is already full, then those threads are going to block because the queue is full, but the queue will never get not full because all the threads in the pool are blocked trying to put things in the queue, right? So this is the context in which you can have problems with fixed size queues leading to deadlock. There are other situations as well. And you can read this little article that talks about thread pool-induced deadlocks. The article is written using Kotlin, but it uses the thread pool executor from Java, since Kotlin can use Java class libraries quite easily. So even though it's not maybe the most familiar syntax, it's easy to figure out what's going on. And the author talks about a couple other ways in which you end up with deadlock from fixed-sized queues. So to avoid that, it uses an unbound queue. And as we talked about before, there are pros and cons to that, right? The downside with the unbounded queue is it can start to consume a lot of resources. OK, so there's a pool of threads that we get from using an executor service implemented using the thread pool executor with a fixed number of threads. There's also another thread, which we'll call the waiter thread, and it runs in the background, and it's going to wait for all the futures to complete. And so we'll see how this is going to get used. But we're going to spawn a thread, and it's going to run some code, and that code is going to wait for the results to come back as they're processed by the threads in the thread pool. All right, that's kind of the concurrency architecture of our solution here. We have a class called PrimeCallable, and as it kind of suggests, it implements the callable interface. And as you recall, callable is parameterized with a type. In this case, it's going to be something called prime result. I'll talk about what that is in a second. And the PrimeCallable will define a two-way means of determining whether a number is prime. So when it's called, it's going to be running in a background thread, and it's going to go ahead and check for primeness. And when it's finished, it'll return a result. And we'll see what that result looks like in a second. So the way it works is that the constructor for PrimeCallable is actually passed a function. This is a Java 8 function interface that maps long to long. And what this is doing is it's going to be used to check whether a prime candidate, which is the other parameter here, is in fact a prime number. And it's going to keep track of that. All right, so we're going to pass in the prime candidate, which is going to get stored up here. We're going to pass in the PrimeChecker, which also gets stored up here as well. This PrimeCallable is going to be placed into the thread pool to run at some point when there's a thread ready to run it. So it'll run in the background. And when it's ready to run, the thread pool will turn around and call the call method, the call hook method, which, as you can see, is going to make a new prime result, which is the return value here. And it's going to check to see whether the prime candidate is, in fact, a prime number. And the way it's going to do that, it's going to apply the function that was passed in here. It's going to apply it, passing in the prime candidate. And so that's going to return the result, which will either be 0 if the number's prime, or the smallest factor if it's non-prime. And that result and the prime candidate, the original value we're checking for primeness, will be stored in something that's called a prime result. And we use the prime result as a way to be able to get the result back to the main thread, the waiter thread that's sitting there waiting to get results. And the reason we have to pass two things is because we need to know what number we were checking, and we need to know the result of the check. So that's a tuple. So it's got two fields in it. Basically, the original number, the prime candidate, and what the result of checking for primeness was for the prime candidate. That's kind of how those classes work. Now, the main activity, which is the thing that's kind of driving all this in Android, is going to have a list of futures. It's going to make a list of futures, and this list of futures will store the results of the concurrent checking of the primality of the random numbers that we're going to check. We're going to have count of them, which is some number, 25, 50, whatever. You can make that a parameter you pass in on the GUI. And so here's main activity. This is the thing in Android that interacts with the user. So we need an activity to interact with the user. We're going to have this list of futures, which are going to keep track of prime results. And here's how the list of futures to prime results gets initialized. This is a really cool, simple Java 8 stream. And so I'll explain how this works. So this stream is going to end up initializing this list of futures to prime results. So the first thing it does is it creates a new random object, which is anonymous. We just make a random object, and we say .longs. .longs is a generator function that generates count random longs between the values of 0 and the maximum value of a long. So it's going to be, count random numbers that are big, probably. So that's going to come out as a stream. And we're going to have up to count of them. We're then going to call a method called map to obj. And map to obj is simply a variant of map, which is going to take the input, which is the previous output from the .longs method, which is the generator method. So it's going to have a stream of longs, random longs. And for each random number that comes in, we are going to create a PrimeCallable. Remember this guy. We're going to make a PrimeCallable. And that PrimeCallable is going to have the random number and something called a prime memoizer. I'll explain what a prime memoizer is in a second. So what we're doing here is map is basically used for every element in the stream for count random numbers. We're going to make a new PrimeCallable object with a random number and a prime memoizer. So what the heck is a prime memoizer? We'll come back and talk about memoizers later. Really, really cool technique, and it illustrates some interesting stateful mechanisms that we use with lambda expressions. But basically what a memoizer is something that's going to cache the results of a computation. So it's a generic class that will cache results. And so if somebody, in this particular case, it's going to be a memoizer that caches longs to longs. So if you pass in a prime candidate and you've already checked that prime number to find out, or you've already checked that candidate to see if it's a prime number or not, the memoizer will remember, it'll memoize or remember the mapping from the prime candidate to whether it's prime, in other words 0, or its smallest factor. So it's basically a cache. It's caching that. And under the hood, it's using a concurrent hash map to do all this stuff. And like I said, we'll talk about it later. If that prime candidate has not yet been checked, right, so we don't know if it's prime, then it's going to call this function here. And this function will then go off and check to see whether that number is prime. And if whatever it comes back with, that will then be stored as the value in the key value concurrent hash map. And this is a really super cool thing. It'll give us a chance later to talk about some fascinating concurrent hash map features such as compute if absent and so on, which is how we're using this. But for right now, don't worry too much about the details. This is just a cache that looks this thing up. And the reason for doing this is if we look up the same random numbers over and over again, we don't have to keep recomputing whether they're primes, because we memoize or we remember what the result was from the previous time. And the other cool thing is this is totally invisible and seamless. So this thing just kind of slips into the stream, and it basically performs a thread-safe cache. Down here, we then use something called Callable. We take the Callable that comes out of map to obj, and we map or transform the callables into something that will run asynchronously in the thread pool. So what we're going to do here is we're going to take the executor service, which if you recall we initialized to be a thread pool that's fixed size. So we're going to take the thread pool that's fixed size, and we're going to submit the callable into the executor service. So this is going to take the output of this map operation, which is a prime callable object, and it's going to submit it to be processed in the thread pool by using executor service submit. This is a method reference. And what's going to happen, of course, is that submit call is going to queue up the callable in the queue in the thread pool executor, and then one of the threads in the pool will pluck that out of the queue and then go ahead and run it. Question? It's a lambda that is, it's mapping callable into something that can be submitted here. Actually, I think that might even be a syntax error. This should probably not have callable arrow. It should just be the method reference. Yeah, thanks for pointing it out. I think I had it done differently before and forgot to update it. So we don't have to say callable arrow. We just have to say mExecutorService : submit, and it figures out how to do the mapping. And that's because it just takes a single parameter, which is the callable. That's the parameter. Okay, remember that particular little trick because you're going to need it for your programming assignment, something along those lines. And after that guy's been submitted for execution, we then go ahead and collect up all the futures that come out of this. So submit returns a future. It takes a callable and it returns a future. So it's a good example of transforming. So map can be used to transform its input stream to a different type of in the output stream. So up here we transformed longs to PrimeCallables. Next we transform callables to futures. And now we collect them all together, and they're going to get stored in a list of futures to prime results. So that's what this thing will end up being, and it'll create this type of data structure. Okay, just some simple Java 8 stuff. You could always, of course, write this in Java 7 with a for each loop, but this is so much cleaner once you get the gist of reading Java 8 functional code. All right, I mentioned before that we also have this background thread that's used to wait for all the results. And the whole purpose of doing this is to not block the user interface thread. Remember, in most user interface-driven or GUI-driven programs, we have to not do long-running computations in the UI thread. On Android, if you ignore that rule, you will get the dreaded application not responding exception, which is described here at this link at the bottom of the slide. So we don't want to be doing blocking operations like computing whether a number is prime or not. We don't want to be computing that in the foreground. We want to do it in the background. So what we're going to do is we're going to have this class called future Runnable, which is actually nested inside of main activity. It implements Runnable, and it's got a run method, which we'll look at in a second, that runs in a background thread, and it basically is used to get the results of the computations. Now, this object, the future Runnable object, is actually stored in a field. And this field is then used to create a thread. So we're making a new thread with the future Runnable object as the parameter to new thread. And then we go ahead and start that new thread. And you'll see everything has this weird thing that says retain state. I'll come back and explain what retain state is in just a second. The reason why we do retain state is so that if someone rotates the phone, the thread is in a different state, so it will not be destroyed when the activity goes away. And I'll talk about that in a second. Yeah, Cole. Yes, so that's called, let's see, I always forget whether it's system or application Hungarian notation. So Hungarian notation is a way of encoding some metadata into variable names to give you an indication at a glance something about the variable name. So this particular approach, which is, so I'll call it Hungarian notation light, basically says if it has an M, it's a field. And the reason you would do that, if you choose to do it that way, and I happen to like that way a lot, is because when you're reading your code and you see something that has an M, you know, that's a field. If you see a variable that doesn't have an M, it's probably either a local variable or it's a parameter. And so sometimes it's hard to know, especially if you're reading code on a slide or a printout. Obviously, if you're in your IDE, you can quickly tell what it is by putting your mouse over it or your pointer over it, and it'll hover and show you where it came from. But if you're reading code like this, it just helps at a glance. The reason it's called Hungarian notation is the guy who invented it was Hungarian. His name was Charles Simonyi. And he's famous for a variety of reasons, not the least of which is for a while he was Martha Stewart's boyfriend. And he also ended up going on a ride on a Russian rocket into space. He was a space tourist. And he was also one of the first employees at Microsoft, so he's worth a lot of money. Interesting guy. I've met him several times, and quite fascinating. But that's a whole other story for another day. OK, so good question. Thanks, Cole. So we create a thread. The thread runs in the background, and we'll talk about why we have this retain state thing in a second. Here's what future Runnable does. So future Runnable is going to stash away the list of futures and the main activity so that this is stored away in a safe, convenient place. And then what it's going to do is when it runs in the background, in the background thread, it's going to go into a loop, and it's going to loop through the list of futures, and it's going to get the results of each future. And this is what's often called synchronous future processing. And the reason it's synchronous future processing is we say f.get, and this will block until that future is completed, until the computation to produce the result of the prime number calculation runs to completion in the background. And so when that finally is done, get will return the prime result. And if it is not done, it'll end up blocking. So this f.get call blocks synchronously until the asynchronous processing associated with the future in the thread pool has completed. So we're going to have this background thread just kind of waiting for the results to finish through the futures. Now, what's this retain state thing? So this is a clever technique you can use with Android in order to be able to make sure that some state survives a runtime configuration change. And the state we want to survive are things like the executor service, the future runnable, and the thread object itself. So those three things we want to not be destroyed every time the phone rotates. Otherwise, we'd have to restart the computations again, which would be annoying. And this uses a little trick in Android called onRetain non-configuration instance, which is quite a mouthful, and getLast non-configuration instance. Horribly named things, by the way. It's very confusing, or at least it's very long-winded. And these are basically hook methods that Android calls automatically to load and store retain state when a program is rotated, when you rotate your application. We'll talk more about this later. It's a very simple thing to do it this way. All right, so that's the core part of the code I wanted to show you. There's obviously other stuff, but the main thing there was we saw the thread pool, we saw how to create the thread pool, we saw how to submit work, which were callables to the thread pool, we saw how to have a background thread waiting for the results to come back via the futures, the list of futures, and so on and so forth. So let's kind of compare and contrast this relative to the earlier example that used the executor interface, which was very simple. So one nice thing is, unlike the original code, we don't hard code the PrimeChecker function. Before, the PrimeChecker was hard coded. So if you wanted to make any changes, you had to go in there with an X-Acto knife and perform surgery on the code. This time, we pass in the PrimeChecker as a function. And that allows us to do stuff like this. If we want to use the efficient PrimeChecker, we can use one implementation. If we want to use the brute force checker, we could do that. And there might be reasons for having 4 or 5 different types of prime number checkers for different reasons. And this way, we can just pass them in as parameters, which can be parameterized based on user preference or phase of the moon or whatever we want to use to control how it works. So this is basically a loosely coupled way of writing the software as opposed to a tightly coupled way. Another nice thing, which probably went by too fast when we talked about it with the earlier executor example, the PrimeChecker example with the executor interface, we've gotten rid of any lexical dependency on main activity in PrimeCallable. And so if you take a look at the PrimeCallable implementation, if you were to look in the code, you would see that there's no lexical dependency on main activity anywhere here. And this is nice because now when rotations occur, we don't have to worry about main activity going away and having to reset it and all this other nonsense. So that decouples the way the code is written for runtime configuration changes. We can also interrupt the code. So if we so desire, if somebody rotates the phone or if they push the cancel button, then we can go ahead and shut things down. And that's because we actually check in our prime number checker whether or not the thread that's the checker's running in has been interrupted or not. So thread.interrupted is a method that's defined on a thread, and it goes and checks to see whether that thread's interrupt flag has been set. We'll talk more about what that means later. But the good news is that you won't just keep spinning blindly as you're pushing cancel and nothing is happening. So it makes the program more responsive. And another thing you can do, and this is pretty cool, we can also set it up so when someone does in fact push the cancel button, we can arrange to call this method, which will shut down the executor service now and also interrupt the main thread. So let's talk about this for a second. This is important. So interrupting the main thread, this is how, and this should be lowercase I, not capital I. So we will interrupt the main thread, and that sets the interrupt flag, which can then be tested to see whether it's shut down. So that's one thing. Shut down now is a way of telling the thread pool, stop doing whatever you're doing, stop processing what you're doing, and get those threads in the pool to shut down because I want to stop. And if you were to look a little further in the code, you could call the await termination method. And because we called shutdown now, await termination will return very quickly because we've actually shut the threads down. The await termination method, which we talked about last time, as you may recall, waits until all the threads in the pool have stopped running. If you do shutdown now, they get shut down very quickly, and so await termination will come back very quickly. If you were to use shutdown in contrast, there's also a method called shutdown on an executor service. And what that does is that says, accept no new work into the thread pool, but let the existing tasks continue to run till they're finished. And because, as we saw, it may take a long time to compute whether a number is prime or not, that could make the GUI very unresponsive, right? You decide I want to cancel this thing, and you hit cancel, and nothing happens, and nothing happens. And you keep hitting cancel, and nothing's happening, nothing's happening. So shutdown now will just make sure that things happen faster. That'll get await termination to be done faster than using shutdown, which will just say, don't take any new stuff in there. A good example of this would be at most stores when it's closing time, they typically lock the door so nobody can come in. But if you're in the store, you can finish your shopping and go out, right? That's shutdown. So the people in the store have to wait around until the last customer leaves. Shutdown now would be like coming in and releasing a pack of German Shepherds to eat the people in the store, right? That's shutdown now. Not necessarily the best way to have repeat customers, but it does get the store shut down faster. There, however, are still some limitations. You always find that there's always pros and cons to everything with almost everything we do because I'm motivating each of the features, and these limitations then motivate the next set of things we'll talk about. So one problem here is that we call f.get in this loop, and that will end up blocking the thread even if some of the other futures later in the list are already done. Those other futures may be finished, but because of the way that the future mechanism works in simple Java, Java 1.5 type of futures, you end up having this problem where you have what's called head of line blocking. So if the thing at the head of line takes a long time to finish, all the other stuff that's already done doesn't get to be processed till the thing that's slow is finished. It's kind of like if you're trying to turn left in a left-hand turn lane. Or let me rephrase that. You're trying to go down a single lane road. There's a bunch of cars ahead of you. One of the cars is trying to turn left into oncoming traffic. Even though you're just trying to go straight and you're not trying to turn, you're stuck behind that car who's trying to turn left because they can't turn right away. That's called head of line blocking. And this is a common problem with synchronous future processing. And sometime later, maybe next fall, maybe later in the course, we'll talk about the completable futures capabilities in Java 8. And they solve these issues because they allow you to do asynchronous future processing, which is much more scalable and powerful. And then the final issue, which you will only partially understand at this point, but I'll fix it later, the memoizer that we have developed for this implementation doesn't allow itself to clean up the values in the cache. So if you run this program for a long time, you'll just make the cache bigger and bigger and bigger, and you might not want that if the program runs for a long time. So we'll talk later when we talk about the scheduled executor service about how you can have a timer mechanism in the memoizer which wakes up periodically and cleans out entries that haven't been accessed in a while, where a while might be 5 minutes or 10 minutes or whatever. So you'll end up kind of bursting at the seams if you don't clean stuff up. Okay, so that's the end of our overview of the Java Executor Service. Hopefully you have a better idea now of how to actually use it.